All right. Let's prove something that everyone takes for granted. It's really not that crazy, the proof. I'm just going to go through it because you should know it. Okay, if you've taken a calculus class, you use this. This is usually called the power rule, right? The power rule. It's really not that crazy to prove it. There's one thing you need to know in order to prove this is the binomial theorem. If you don't know the binomial theorem and you wanted to continue taking math classes, I suggest you learn it. I've gotten reprimanded myself for not knowing it, and because of that, I'll never forget it. So, what does the proof look like? Let's write out the proof. It's just computation. There's not really like crazy logic or anything. Okay, we just use the definition of the derivative. So let's let f of x equal x to the n. By the way, this is only really true. You have to sort of do a generalization here. This is only really true. What I'm about to do is for n, which is a natural number. Okay, n is a natural number. So what is the derivative? That's what we're looking at, the derivative, right? The derivative. So what is f prime? F prime of x is equal to the limit as h tends to 0 of f of x plus h minus f of x, right? F of x plus h to the n minus f of x, x to the n, all divided by h. Using the definition of the derivative. Definition of derivative. Nothing too crazy. Difference quotient. Right? Hoping you know how to do that behind. Alright, so this is where I need the binomial theorem, because now if I want to expand the x plus h to the n, this is the binomial to a power, hence why it's called the binomial theorem. X plus h to the n is equal to n choose 0, x to the n, h to the 0, plus n choose 1, x to the n minus 1, h to the 1, keep going. The second to last term is going to be n choose n minus 1, x to the 1, h to the n minus 1. And the final term is going to be n choose n, x to the 0, h to the n. I still have the minus x to the n, so quite annoying that I ran out of room. I ran out of room there, but that's the way it goes. Maybe I'll just cut this part out because that annoys me. So let's try that again. Using the binomial theorem, h tends to 0. This is n choose 0, x to the n, h to the 0, plus n choose 1, x to the n minus 1, h to the 1, plus, keep going, n choose n minus 1, x to the 1, h to the n minus 1, plus n choose n, minus x to the n. There, I barely fit it. Minus x to the n. All over h. All over h. So just to reiterate here, this is what happens when you expand the binomial. This right here is x plus h to the n. And then I have this x to the n over here, so it's still there. It's still there, don't forget about that. Now, we're pretty much there, actually. This is the limit as h tends to 0. Now, a lot of these binomial coefficients are annoying to find. You have to use factorials and things like that. But some of them are nice. And there's also some symmetry. So n choose 0 is 1. So this is just x to the n. because h to the 0 is 1, plus n choose 1 is n, x to the n minus 1 times h, plus, go all the way down here, n choose n minus 1 is the same as n choose 1. So this is also n. This is x h to the n minus 1. N choose n is the same thing as n choose 0. And how many ways can I choose n things from n things? One way. So 1 times x to the 0 is 1, h to the n minus x to the n. This is looking good. This is looking quite good. This h is upstairs. Leave that down there. Leave that over there. Okay? Look what I can cancel. X to the n, x to the n. Now, something happens here that always happens actually. Whenever you compute a difference quotient, everything in the numerator, as long as it's an algebraic expression, everything in the numerator that does not contain h should cancel. Furthermore, after that cancellation, you should get another cancellation in h. So an h here, and all these terms upstairs have h as well. So I'm going to cancel this h here with that one. All of these inside have h's. I'm going to cancel those. I'm going to cancel one of these and one of these. If you think about this for a second, we're done, because look what's going to happen. I'm taking h to 0. If I take h to 0, all of these, this is the only one that doesn't have h. This is the only one that does not have h. All of these are going to be gone. Take h to 0. This is equal to nx to the n minus 1. That completes the proof. Fill in the details if you like, but you should be convinced. All right.